Hello everyone. Let's begin with a spark, literally. Imagine you have common salt, sodium chloride. It looks so boring sitting in your kitchen jar. But when you melt it and pass electricity through it, something magical happens. It splits apart. That splitting, my friends, is electrolysis. So, what exactly is happening? Electrolysis is the decomposition of an electrolyte, like molten sodium chloride or aqueous copper sulfate, by the passage of direct current. The ions inside the solution start moving like excited party guests. The sodium ions, written as Na with a plus sign, rush towards the cathode, that's the negative electrode, and happily gain an electron. In other words, sodium plus one electron becomes sodium metal. Meanwhile, the chloride ions, written as Cl with a minus sign, sprint towards the anode, the positive electrode, and lose an electron. In simple words, two chloride ions together become one molecule of chlorine gas and release two electrons. When you combine both sides, the overall reaction is two units of sodium chloride decompose to form two atoms of sodium metal and one molecule of chlorine gas. Remember, electrolysis is always a redox reaction where reduction and oxidation are happening together, one at each electrode, dancing at opposite poles. Now, let's play a little game of opposites. Electrolytes versus non-electrolytes. Electrolytes are compounds that conduct electricity in their molten or aqueous state because they split into ions. For example, hydrochloric acid, sodium hydroxide, or copper sulfate. Non-electrolytes, on the other hand, are party poopers. They don't conduct electricity at all because they don't produce free ions. Think of alcohol, kerosene, or sugar solution. No matter how much current you pass, the bulb stays stubbornly off. Here's the key. Conduction depends not on water itself, but on the presence of free ions. So while salty water lights a bulb, pure distilled water does nothing. That's why you never hear anyone charging their phone in sugar syrup. Let's take this a step further. Not all electrolytes are created equal. Strong electrolytes like sulfuric acid, sodium hydroxide, or sodium chloride dissociate completely. Drop them in water and boom, you get a full army of ions. That's why they make the bulb glow brightly in an electrolytic setup. Weak electrolytes like acetic acid, ammonium hydroxide, or carbonic acid are shy. They only partially ionize. Their few ions give you a dim glow at best. So in the lab, the brightness of the bulb literally tells you how strong your electrolyte is. Just imagine, acids and bases are auditioning for a role in your experiment, and only the strong ones light up the stage. Okay, now, where does all this drama unfold? In the electrolytic cell, the theater of electrolysis. Picture a container filled with the electrolyte solution, two electrodes dipping inside, and a battery connected across them. The anode is wired to the positive terminal, and the cathode is wired to the negative terminal. Sometimes we use inert electrodes like platinum or graphite, but in some cases, reactive metal electrodes join the party. The current flows through the circuit and ions start migrating, cations towards the cathode, anions towards the anode. That's when the redox show begins. Without this carefully wired stage, you wouldn't get any of those magical transformations we rely on, from purifying copper to electroplating jewelry. Let's zoom into the real heroes of our electrolysis story, the electrodes. At the cathode, that's the negative electrode, the positively charged ions or cations arrive hungry for electrons. Think of sodium ion, spelled as Na with a plus charge. It grabs one electron and gets reduced to sodium metal. In chemical language, Na++E- gives Na. Copper ions behave the same way. Gain electrons, become copper metal. Now switch to the anode, the positive electrode. Here, the negatively charged ions or anions come to lose electrons. A classic example is chloride ions. Two chloride ions, each spelled as Cl-, give up 2 electrons and pair up to form chlorine gas. The equation 2Cl minus 2 electrons gives Cl2. And here's your superhero memory trick. OILRIG. Oxidation is loss, reduction is gain. So anode is always oxidation, cathode is always reduction. If you mix them up in an exam, your marks will get discharged faster than ions racing to the wrong electrode. Now let's meet the real movers and shakers of electrolysis, the ions themselves. Anions are the negatively charged ones, and just like negative vibes, they're naturally drawn toward the positive anode. When they arrive, they happily dump their extra electrons. That's oxidation in action. Take chloride ions for instance. 2Cl minus ions lose 2 electrons and form chlorine gas. Written out, 2Cl minus 2E minus gives Cl2 gas. Cations, on the other hand, are the positive crowd. They adore the negative cathode because opposite charges attract. When they reach the cathode, they gain electrons, and that's reduction. A classic example is sodium ion. Na++E minus gives sodium metal. And here's a little memory joke to nail it down. Cations are cute. They always go to the cathode. Anions are angry. They rush to the anode. Once you fix that picture in your mind, you'll never mix them up again. Not in the lab and definitely not in the exam hall. So let's wrap it all up. Electrolysis is nothing but electricity driving a chemical change. Electrolytes are the conductors. Strong ones dissociate fully, weak ones only partly. Non-electrolytes simply refuse to play. The electrolytic cell is our stage, with anode and cathode as the main actors. Cations are reduced at the cathode, anions are oxidized at the anode, and all of this is one grand redox show. If you ever forget, just remember, electrolysis is electricity forcing chemistry to bend to our will. From extracting pure metals to powering industries, this simple principle is everywhere. And that, dear students, is why electrolysis is one of the most electrifying chapters in chemistry.